I bought this meter back in the early 90s, perhaps even 89. I can't find the docket for it, but I do know that I blew it up when I bought this meter around, so that's what, the 31st of October 1994 is when I bought that meter as a replacement for this, because I blew it up on a high voltage source. I made myself a high voltage probe, and I messed up in the return paths for the higher the 1 gig ohm resistor string, and it arced across and blew up the meter. And specifically, it blew up the chip here. If you compare those, the old chip and the new chip, you'll see that the old chip actually has a more recent manufacturing date. So what's that? The 6th week, is it? Yeah, 6th week of 1990. So it's 90 is the year, and that's the next two is the week. And this one's 8845. So this one, I bought this in 94, so it's clearly old stock. The plan was that I was working enough, like in a lot of the indicators, what do they call them, annunciators, and the decimal points weren't working, and I tracked it down to this chip being dud, this hybrid module on here being dud, but it was working well enough to give me an LCD display, 7-segment displays, but none of the decimal points and that sort of stuff. So I then decided I needed another meter, and so I thought, look, let's try and bring this thing back into line. So I started off trying to calibrate it, and I did go through a calibration process. And as I reached the end of that calibration process, I started to look into more of the circuit and understood a lot more than what I did at the time. And it's become apparent that the ICL chip, or in the case of originally the TSC, provides power supplies or power rails for various aspects of it. And so one of the application notes is that if you use the test pin, you can provide milliamps, like single, 2 milliamps. I think that the data sheet said 1 milliamp, but not to draw more than 1 milliamp from that test pin to use it for driving your LCD annunciators and decimal points. In fact, I think they talked about decimal points only and not annunciators. And so it left me confused as to why they needed this hybrid package to begin with. And so I noticed that the test signal was really low, and in comparison, the 7-segment drives were significantly larger in amplitude than what was coming off the backplane, and that's when I realised that this chip, whilst it was faulty, it's faulty in a way that draws quite a bit of current and drags down that test. And so, if you look carefully, you'll see that I've cut that track going to pin 2, I think it is. Yeah, pin 2 on the hybrid. Pin 1's at this end, and pin 2's. And I've cut the track, and that immediately brought the backplane signal. I had that little wire that broke off over here, brought the amplitude of the backplane up. So the problem I have here is that there is no reverse, there's no out of phase signal for the decimal points and the annunciators, all of those little elements around the edge, and that is coming from that hybrid chip there. And there seems to be multiple, there's at least 3 outgoing signals from here, so I'm couldn't figure out easily what that actually meant. Sorry, I'm looking at the wrong chip. There's one here. I couldn't figure out why they needed so many pins to begin with, and all the rest of it. And so I thought, what I'll do is that in taking some photographs, I bent the chip and the damn thing broke most of the leads, and I thought, well, you know, that's actually motivating me to actually completely remove the module. And so the plan is to use some acetone, put it into a little glass jar, put some paper or some sort of some sort of sealant on the lid, because the lid's plastic and I don't want the acetone to dissolve the lid. I might use foil, and just sort of take that chip off, drop it in the base of the glass container, and just let it sit there for, I think one of the guys on the internet said he left it in there for 3 days, and that should then dissolve the epoxy off here. And so I will do that, and then try to reverse engineer the circuit on here, with the goal of getting this meter back up and running again. Now, you know, fair enough, you can go and buy a new meter, replacing this one for a lot less money, but it's a good learning experience. I've certainly learned a lot about LCDs and the ICL chip in the process, and so you just need at the end of all of this tinkering and learning, I'm going to have a meter that's working again, hopefully. Okay, so I'm just going to do a little bit of an investigation on the annunciators, the LCD indicators. The way the LCD is supposed to work is that you have a back plane, and rather than apply a DC, which can essentially you drive it with AC signals. And so, if you want the segment, the element to be on, you drive that segment and the back plane out of phase. So they're out by 180 degrees. I think it was 180 or 90 degrees. 180 degrees. Yeah, the segment's driven at the same frequency and amplitude, but are in phase with the BP when off. And out of phase when on. Right, so I've got this going into channel 1. That's a good point. Start recording on the capturing. Okay, so that should be capturing now my oscilloscope. So I've got pin 21 going into channel 1. And if I connect that to back plane, you see that it's in phase. The hardware clock in the bottom right on the screen tells me it's 47, and the oscilloscope's calculation of what it sees on screen is 48. As you can see in the bottom here. So if we go to one that's out of phase, go to a segment drive, you can see it's out of phase, and there's quite a discrepancy in the voltage. So that's coming off the LCD. But on the other side, that gets fed into resistor packages here, into resistor packages over here. So you can see they're in phase, and these wander off in between these holes, and through to the switches, the switch contacts, and eventually get fed back up through here. Alright, so we're looking at that screen we've got 0 is in the center of the screen, and because I've got the earth on the common effectively. So when anybody who's familiar with the ICL chip, it has a plus and minus, and it effectively provides various rails. One of the rails that it provides is a common, which is then connected to your common input on your multimeter. So that's the volts, ohms, common. These are 2 amperages. I've effectively got that plugged into there because I'm just using the capacitor measurement one, and there's a direct short between those 2 points there, so that just makes it easy for me to clip onto. But as you can see on screen, the back plane is at the battery's negative terminal, right? So that's why it's actually below. Okay, so just going to use my crappy old hand desoldering pump, and as you can see, I've flooded the top side because probably there was only 2 pins actually mechanically retaining it. I can't remember which 2 pins they were, so I'll just go through the lot of them. Wait till the other side melts. So it's obviously sucking up the broken pins in the process of doing that, so I'm going to have to figure out if I actually repair this hybrid module, how to reattach those pins, although I suspect I'm going to have to make another circuit, not as opposed to repair the hybrid. But I need to get the hybrid. I need to reverse engineer the circuit on my hybrid, and depending on how bad it's damaged. Now these hand soldering tools, desoldering tools, you need to service them. So I've replaced the Teflon bit on there, and then cleaned all the crap out of there, cleaned the crap out of the O-rings, greased the O-rings, cleaned up the locking bits and all that. So this thing's probably best part of 30 years old. But if you maintain it, it can work. Doing this sort of through-hole type work, sucking it out on the opposite side, that's the easiest and preferred way to use this type of a tool. Desoldering and using this hand tool on the same side is nowhere near as easy. As you probably notice, I'm trying to get the tip flush with the hole. Obviously, to get a hand a proper through-hole desoldering tools would be preferred, but they're like 200 Australian bucks or so, and I've not required it, and I'm not going to buy it just for this project. The need for through-hole stuff has reduced a lot these days. So what I'm doing is I'm just pumping the desoldering tool, because what happens is inside the desoldering tool is like a spring, and giving it a shake. You just need to get all the crap out of it. I use an old cut open envelope to collect it all in, and then throw it, dispose it. So that's convenient to have beside me on the bench, and just keep the desoldering tool inside the envelope, so any crap that comes out is contained. So the end result of that is, I've got this in a vise by the way, and I've put some paper around it. So that's the end result. I'd be surprised if that comes out. Yeah, there's probably still a little bit of solder. And I don't want to break off any pins that are existing, so 1, 2, 3 pins still in the holes. Whether they're still attached to the chip is another thing. Got the soldering iron at about, what is it, 340 degrees Celsius. Whoop, used to work. Okay, that pin's not attached, just fell onto the paper. So that was in the hole. So the pads are really small, and with through-hole plating on small pads like that, and it's only thin weight. It's gold plated. There we go. So there's only two pins left attached to the hybrid. The rest of them all broke right at that junction where it meets the main board. So now that's just going to go into some. I'm going to drop that into my little glass container. Just layer it just so that it sits enough. I don't know whether I'm going to completely flood. It depends on how it's going to evaporate, if it evaporates. Specifically, I need to make a good seal between the plastic lid and the glass jar. So I'll do some tinkering off camera and come back and show you. Okay, so I think I've come up with a plan. So what I'm going to do is just put some foil in there. It's not neat, but the main thing is going to cause a seal around there. I'm going to use this wax, and I think what I'll do is I'll just heat this glass with my heater, my butane heater. You can see the water in the exhaust on the hot air tool. Yeah, so anybody who asks, if you go, I bought this tool a few years ago. It was just an impulse buy from Aldi, and I bought it on the basis that I might need to use, like it came not in with the hot air attachment, but it came with soldering iron bits and stuff like that. I thought it'd come in handy, for occasionally for when I need to use it in the car. Didn't want to have to worry about trying to get power and things like that, sort of emergency type arrangement. I found that I've been using this hot air tool more and more, and I'm probably going to invest in a proper hot air workstation. We'll see, but for the moment it's sufficing. Is that hot enough? Is it melting? So the trick here is to drop this inside and just being cleaned, pour in enough to get the job done. I want that chip the other way around, like that. And get past the child-proof lock on it. I mean, I could have sworn I had more in there. It's even in this container. This is actually a surprise when I bought this. It actually is a plastic container, but because the other times that I bought acetone, it's always been like in metal lids and cans and all that sort of stuff. And just leave that. I'll put that in a safe spot and leave that for a few days. Well, I'll check it tomorrow and all that sort of stuff. But the main aim is to get that epoxy off without damaging the circuitry and pulling the components off. One of the things I ran into whilst doing my initial calibrations were is when I got onto the frequency range. This supports a 200 kilohertz and a 20 kilohertz, and I've marked that because I had problems whenever I changed it to the 20 kilohertz position, pretty much from either direction. You had to muck around with the switch to get it to work. So taking a look on what I'm calling the input board with the jacks and all the rest of it, that connects to the main board via some pins there and at the front here. The way that this works is it has a rotary disc, and these travel. You'll notice that this has spring loaded and it has two sets of contacts on each of those, and these travel in different paths, different tracks, and so they're arranged in the rings, so you have a pair per ring. So those two is one, the next two is the other, and next two, and so you have four sets marrying up with this, and similar on the other side, and they travel in different positions. You notice the distance from the center. So these two are doing let's call them the first and third, and this is doing the second and fourth. Sorry, I had a shot. This is doing the inner ring. And that's the third ring, that's the second ring, and that's the fourth ring, or the outer ring. Yeah, so the problem is that on here, when I tracked it down, this pair here, this is for your 20 kilohertz, and that's your 200 kilohertz, and the 20 kilohertz, there's a via right there, and the contact was obviously sitting in or being perturbed by the hole. So I went in through the other side and then started putting in some solder and just carefully controlled how much solder flowed through to the other side. The idea was to not have it spread out too far, and initial testing of that has shown that it's actually improved quite a bit. I did the second via just as a matter of course, because I wasn't completely sure where the physical contact is in relation to the pad, but based on, one assumes that the manufacturing tolerances are pretty close, So one would assume that's the position for the 200 and that's the 20, and that's right in the middle. See, those two V's line up, but that one is obviously in the active area of the contact, and so I think I only needed to do that one, but you know. So initial testing has shown that that's actually improved reliability, so we'll just, going forward, we'll see, we'll keep an eye open for an issue with the frequency stuff. Okay, so it's back together again without the hybrid package. Anything missing out of the side there. I think that's set to frequency at the moment. So the main thing I wanted to see was whether all of these indicators which I have around here are all on the same back plane and just using my one of my meters in continuity mode. I just hooked that up to the common input on the meter, and then just use the positive lead. And I think there's about like 1 volt or something like that positive on this in this particular mode on that meter. And as I go around, you start to notice things light up. So indicators coming on. Yeah, so decimal points are around here, I think. Decimal, no. So obviously, probing around like this the result will change depending on the position of the switch where it is at currently. And that's the one after the first position. That's second position. That's third position. It's back to second, so that's third position. That's second. So I can't find the fourth position one. It'll be around there somewhere. I suppose if I was sensible, I'd be going off these resistor packs, wouldn't I? Yeah, so that gives me, so what they're obviously doing is they're taking the backplane signal out of here, they're feeding it into this device, and this device is then the hybrid which I've taken out is manipulating the signal, and it must be inverting the signal with a buffer or some kind to give us an out of phase signal to get us to turn on one of the segments. So what I was doing there, the backplane is switching and I'm providing a positive polarity, a DC polarity to one of the elements as I'm touching the probe, and that's giving the presenting that particular element on the screen, but we've now got a DC, at least on one plate, if you want to call it that, on one element, and the backplane is switching polarity. I'm not sure that's sustainable. I need to read up a bit more on LCD technology to find out whether that's an issue, because technically we're not providing a constant DC source for it. But what we are doing is we're switching element on and off, as opposed to when you switch both phases at the same time. You're providing the same electric field strength. It's just that the polarity of the field, the electric field is changing. But as from the perspective of the LCD material, the liquid crystal material, I don't believe that matters. But if I'm switching the liquid crystal element on and off, I'm effectively introducing flicker. Not that these would react fast enough, because being a capacitor, they will take time to change. So yeah. Okay, so I thought I would just measure how much capacitance on the LCD there is. So I've set up a little mirror down here to look at the display here. And I've mapped out some of the connections. So I know at this end we've got at least one of the back planes. So we've got a back plane there, a back plane there, a back plane there, and then some back planes over here, 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 and here. So, and there's little cutouts here and here. So the question here is which of these back planes marries up. Change the frequency to something manageable, like 100 Hertz. If I drag my continuity, yeah, you can see the various indicators and segments and dots coming up. Stop moving. So I'll just use my capacitance meter and measure roughly what sort of capacitances we're talking there. I don't think any of the screens will light up in the elements. I'm going to do this so that you can see the meter. 43 picofarads, 70. So yeah, I basically just got a pencil and scribbled on the contacts on there, and then cut it off and just stuck it on there, roughly aligned it, and it's obviously moved. But you get a rough idea of where the tracks would be. Only 8 picos. I've set it to 100 Hertz, so if there was enough drive voltage you'd see it, but I think it's only half a volt RMS, so it's not going to be enough to light up the segments. I've been looking at the meter, not the LCD, and the reflection in the mirror. So I can't see any obvious signs that it's lighting up. Anyway, proves the point.